thank you all for being here. Let's start directly without any delays. With the point we have stopped last time, namely on a different direction on challenging the Kerr hypothesis, Kerr paradigm, namely changing the theory of gravity, including more geometric terms, together with special coupling with matter fields. And the main focus of this last session, last part of my talks, will be on Blackwall scalarization, a subject which enjoyed a lot of attention during the last 5-6 years, with a number of new, qualitatively new results in theories of gravities. So what we are doing is to supplement the usual gravity action. We have Einstein gravity, our matter fields, and we add here an extra term to the action, corresponding to a scalar field, which normally is taken to be real, with a non-standard coupling, non-minimal coupling, but a non-standard one, with other objects, with another object, built in terms of metric tensor. And usually people take this extra piece to be the Gauss-Bonnet Lagrangian or the Pontryagin density, so-called Chern-Simons Lagrangian. Both these terms we mentioned already during the last lectures are special. Without a scalar field, they do not contribute to the equations of motion, topological objects in 4 dimensions, or more standard to the Ricci scalar, in which case if f of phi is just phi squared times some constant, we are all familiar, it's just a non-minimally coupled scalar field, real scalar field. And one can attempt to classify such models based on a simple criteria if general relativity solutions, eventually coupled with other matter fields, are inside or not. So this is the wave, the scalar field equation, resulting from the previous action. And depending on the properties of this function f, which couples the scalar field with this geometrical invariant term, geometrical term scri, this one, you may have class 1 solutions in our terminology, or a dilatonic type, where vanishing scalar field is not a solution. And we are all familiar with the case of Gauss-Bonnet dilaton. Last lecture, previous lecture, with this type of representative example, exponential just of phi times some arbitrary constant. And Schwarzschild, in this case, or Kerr, is not a solution. So once you go to dilatonic Gauss-Bonnet, for example, the general relativity solutions, vacuum solutions, are not there, are not recovered. So you have to go outside the GR. So this kind of coupling was already known in literature, studied by many authors. What is new, and people realized only recently, the situation can be more complicated. If you are liberal enough to allow for non-standard couplings, subject to this property, so taking the derivative of this function at phi equals 0, you can see if this is 0, then phi equals 0 is a solution, independent on the precise expression of this term here on the right-hand side. And one representative example is so-called Gaussian coupling. And then For phi equals 0, curl is inside, and possibly more general solutions of general relativity coupled with other matter functions apart from phi. So it's a new possibility to obtain a theory with two different classes of solutions. Now, this is not, the concept of Blackwall scalarization was somehow in the air. People were discussing it, I think, in the early 90s for neutron stars, in particular these two authors, Damor and Farese, but not for black objects. So it was introduced in a rather different context. And only 6 years ago, people realized that you may have also Blackwall scalarization based in principle on the same mechanism. So this is the scalar field action with this non-zero coupling. And then if you take a small expansion around the vacuum of the model, which typically it's taken to be zero by using a field redefinition, then this results in wave equation on the field for the scalar field, Klein-Gordon equation, but this time with effective mass, which depends on the precise expression of this function, source function scribe. Now, what is new, different from our models of hairy black holes we've seen before, is the possibility that this mu square effective, so the scalar field gets an effective mass sourced by this term, mu square can be negative in some regions of space-time. And then you have a tachyonic instability. It is this special feature which circumvents this Bekenstein argument, this type of identity we have derived together in the first lecture. So when integrating over all space, because this part has no definite sign, and in particular may take negative values in some regions, then it is not guaranteed that this integral is strictly, this integrand here is strictly positive. And this is the mechanism circumventing the Nauher theorems, formally speaking. And again, let me emphasize dilatonic coupling. The standard one you obtain from string theory and so on doesn't work, does not support this mechanism, and you have to postulate more unorthodox, non-standard couplings with this supporting this feature. Basically, this coupling function should possess an extrema somewhere. Shouldn't be a standard one. Now, why it's so interesting? Because then you have two different classes of solutions of the theory. You have first the fundamental solutions. The ground state of the model are the GR black holes, are inside. And then you may have solutions with an excited scalar field, so-called scalarized black holes. And they possess a variety of interesting features, and in particular, in many examples, they are thermodynamically favored. They could be also stable, and it was a new development. Now, what about possible models of scalarization? First, this scalarization can be triggered out by a Gauss-Bonnet invariant. I recall that the Gauss-Bonnet invariant for Schwarzschild black hole, for example, is strictly negative. So you get automatically a tachyonic mass for such models with a non-trivial coupling with scalar field. And yeah, it was 5 years ago, I see. So there were 3 papers published almost the same time following these ideas. All of them entered PRL. Then you can get scalarization due to coupling with the Chen-Simons invariant upon 3 eigendensity. Here there is still some work to be done. It's technically much more complicated. Then you can get scalarization because of the non-minimal coupling with the Ricci scalar, and there is some work in this direction. And finally, this is not necessarily restricted to be induced by the coupling with a geometric invariant like these three densities. You may get exactly the same pattern, many similar properties by postulating non-standard coupling of the scalar field with other matter fields, in particular with Maxwell. So this is the Maxwell scalarization. It's the same spirit, many similar results, as I said, but technically it's much simpler because you are just solving a version of Einstein dilaton equation, a more complicated version somehow, but it's one order of magnitude or more simpler than coupling with higher order derivatives, geometric terms like Gauss-Bonnet or Chern-Simons. And then there is nothing special in the end with scalars. You can use the same ideas, extend for other matter fields. We're trying to promote the same mechanism for vector fields, even for spinors. So and there is also similar mechanism in the same spirit even for spin 2, and I have a slide at the very end. So people are talking, for example, about vectorization. So just exciting the vacuum via non-trivial coupling of the matter fields with some other invariants. Now, I have a few slides about generic features of scalarized black holes, trying to summarize, compile the emerging picture, and what is new for such solutions. At least this is my subjective choice of most interesting feature. First one is a kind of mode democracy. In such an approach, you have configurations forbidden by usual electrovacuum theories or for class 1 models with usual standard, with a standard coupling, like dilatonic-like coupling of the scalar field. You may have, one finds black holes which are static and not spherically symmetric, or even static and without continuous symmetries, with discrete symmetries only. So the rotational symmetry is broken. The key point here is that this mode instability is not restricted to the spherically symmetric mode only. All modes, when doing a standard expansion, in terms of spherically symmetric, spherical harmonics, for a spherically symmetric background, let's consider, for example, the case of a Schwarzschild background, which gets scalarized. Then you have a mode equation, zero mode equation for small perturbations. And what is new here, all modes are relevant. You may find similar, same type of solution. You will find same type of solutions for beyond, not only for radial mode, but even for higher modes, for dipolar, quadrupolar, and so on. And they will emerge from some GR set of solutions, which are inside from Schwarzschild in our previous example, and all of them are relevant. Technically, simplest set of scalarized solutions are spherically symmetric, but in principle, all modes are relevant. And the nonlinear continuation of modes with non-zero LM will result in black holes with a non-standard horizon shape, because all symmetries are, continuous symmetries are broken. So that's a curious feature of such models, which still needs to be further explored. I have a few more details in a while. There is another generic feature, which is interesting. Usually in such models, the hairy black holes are thermodynamically preferred. What I mean, for the same global charges, in the spirit of the no-hair conjecture, if you compute mass at infinity or mass and electric charge for a different type of models, the configuration extremizing entropy, maximizing the entropy will be the hairy black holes. This is usually the case, but not always one has. There are also exceptions. It's interesting. And one more feature. For some models, it was possible to do fully dynamical evolution of scalarized black holes. And they are stable. First, they are shown, some models were shown to be stable in linear perturbation theory when doing a mode analyzing, at least for spherically symmetric case. But they were shown to be stable in at least the case we shall discuss next with Maxwell scalarization. And they also can appear dynamically. If you put some perturbation around one of the general relativity configuration, go to such a models allowing for scalarization. It was possible in some cases to show that this perturbation will grow, and after a while everything will settle down, will stabilize around a hairy black hole. So usual black hole with some clouds, some environment consisting in scalar field. Yes, please.
I'm just curious because you said in the slide before that you are comparing to see who's entropically favored for the same global charges. So during the dynamical formation, there can't be a reason why these global charges changes in such a way that you should compare not a black hole in a hairy black hole and the seed black hole with different global charges. So are you sure that you are comparing exactly the same thing?
Somehow we are mixing the things here. There is no dynamics. We are just taking two stationary or static solutions of the same model. The evolution did not, yeah. That's a usual comparison, and one may take many times in general relativity. You don't think about the endpoint here, how the solutions were formed. You have a solution, you have a theory with two classes of static or stationary configurations. One of them is a bold black hole, usual GR1, and then another one is something with some hair around. And then you are just comparing. I think based on this argument, one could try to come with some understanding of the dynamical evolution and so on. But here we are just comparing, nothing else. And the second point in this dynamical evolution, I think it was almost conservative, basically conservative, this kind of evolution, similar to superradiant instability of Eastern Pretorius. No, just wait 2 slides. You will see. That's the point. That's the point. That's the point.
Some part of the parameter space, these simulations justify what Eugen is saying. It's conservative, Prof. But in some other parts, it's not. You're right. Then your line comparison does not.
Just to wait. Yeah. So to make it more precise, I decided to include several slides on the simplest example, in my opinion at least, of black hole scalarization. I will not put Gauss-Bonnet or Chen-Simons. It's technically extremely complicated, and not all details will work out. But if you consider such a simple model with a non-standard coupling between scalar field and Maxwell field, it's a generalization of the usual Einstein-Maxwell dilatons. And it's technically much simpler. It's a kind of toy model. One can do a lot of things. The numerics is standard. You don't have problems with hyperbolosity and so on. And also it was technically possible to construct several classes of new classes of solutions, which for Gauss-Bonnet or other models with a non-trivial coupling with curvature invariants are not yet on the market. It's much more complicated. So here, let's take this theory, Einstein gravity, scalar field, and then Maxwell field. But the scalar field and Maxwell field see each other in a non-standard way. It's not the usual exponential dilatonic coupling, but it's something which satisfies this property. You can take 1 plus phi square work, but most of our work was exponential phi square. Now, if you put phi equals 0, you have Reissner-Nordström inside. And in fact, even Kerr-Newman, all electrovacuum solution, well, that's the only electrovacuum solution, in fact, which is without pathologies. But apart from that, there are also scalarized black holes. So configurations of an excited scalar field. And the beauty here, it is possible to get some analytical results, which was not possible for more complicated scalarization. So for example, we have a closed form expression, quite simple in terms of Legendre functions of the zero mode. And you can do computation, find, based on this exact solution, what are the unstable Reissner-Nordström black holes developing scalar hair around. That's one feature. Then, I mentioned before, let's take some expansion of some arbitrary time-independent scalar field in terms of spherical harmonics. We have the mode equation for this radial modes. And then you can see this is the effective mass function, which is fixed in the end by some arbitrary dimensionless coupling constant here, which appears in the coupling between scalar field and Maxwell. We are postulating it. And then electric charge of the black hole. And trying to answer partially your question, if you do numerics, this is quite simple as compared to other models of scalarization. You can even discuss the full domain of existence of such configurations. So for a given coupling constant alpha, so this is a number, fix it. And then the black holes, hairy black holes, we bifurcate from a given Reissner-Nordström configuration. So here we are plotting the whole set of solutions as a function of the ratio Q over M, this reduced charge. Reissner-Nordström exists in this band below 1. They fill all this area for any alpha. These are the GR or electrovacuum, if you like, solutions. And they fill all this domain. And part of them, for a given alpha, it's just one single configuration, which get a continuation excitation of the spherical mode. I emphasize just the L equals 0 mode, the spherical one. So the nonlinear continuation of these zero modes, which are known in closed form, results in hairy black holes. And you can continue this set of solutions up to a set of, here on this plot, it's a red line, critical set we call it, which is singular. And now you can see this usual bound Q over M equals 1 is violated. You can get overcharged black holes in such models. And this violation, depending on the value of alpha, this coupling constant can get extremely large. So let's see another lesson from such models, like with Kerr last time. The bounds we knew from GR or electrovacuum GR solutions are no longer valid, are not universal. One cannot take it for granted. Just, if you like, some features of a given theory, but they are not universal. And now, this black hole, to answer partially your question, these black holes will never appear as the endpoint of this instability, only here. So if you take some cloud in this point, the mass and Q will remain more or less the same. This process is conservative, but you cannot form via this process overcharged black holes. I think this was also the findings of our group with Nico, no? Okay, so this is one more point. What about higher modes? As I said, there is some mode democracy. The spherically symmetric case is not secret here. This is not guaranteed, because in electrovacuum, I think with a dilatonic field, there are only spherically symmetric black holes when going to the static case. But for this mechanism, for scalarized black holes, this is the curve showing the instability of spherically symmetric Reissner-Nordström black holes with respect to higher L. So this is the spherically symmetric case. This is the dipolar and quadrupolar regions of instability. And the nonlinear continuation of such modes with a non-zero M, quantum number M, which enters the spherical harmonics, real spherical harmonics, will result in static black holes without, which are non-spherically symmetric, and even more, they don't have continuous symmetries. Just one single killing vector. And here we put some results of numerical computation. One curious feature here, if we restrict to the L equals 1, L equals 2 case, these are these are set of solutions in the end, all these dotted lines. And they all bifurcate from the same critical Reisner-Nordstrom black hole, because winding number M does not enter the zero mode equation, so only L matters. But when doing nonlinear continuation, M starts being important. And in this sector, the entropy of black holes is maximized by the configurations which are cubic, the cubic black holes, which is a curious feature. But when scanning the full parameter space, I don't have a slide. However, the spherically symmetric, at the level of the full set of solutions, the spherically symmetric black holes, Harrier black holes, still maximize the entropy. But within this restricted set of configurations, for given global charges, there are configurations, at least locally in that part of the domain of existence, there are the configurations without isometries, the black holes without isometries are maximizing the entropy. And it is an interesting numerical problem. The methods are similar to what George was teaching us during his lectures. It's the same numerical method, but this is a simple enough ground to play, to try to construct such configurations. And in fact, I think this was the first example for asymptotically flat black holes in 4 dimensions, which showing that there are other classes of solutions beyond the static sector. First example of static black holes in a model of gravity coupled with other matter fields, which are static and non-spherically symmetric and possessing only discrete symmetries in fact, which were constructed non-perturbatively. So that's a technical result showing that, again, one cannot take for granted the basic results from electrovacuum case. The picture is much more complicated if you go to more exotic models, in particular for scalarized black holes. And, well, perhaps the best motivated example of scalarized black holes are found in a model where you couple the scalar field, just the Ricci scalar. It's like, we have seen this non-minimal coupling in many different areas. It exists for quantum fields on a curved space-time. There is a special value of this parameter psi, such that the theory becomes conformally invariant when changing the frame. And there are various reasons to expect the presence in the action of such a term may come from quantum corrections. But the problem with scalarization is that R should be non-zero in order to excite this scalar field, which is not the case for the electrovacuum black holes. For Schwarzschild is 0, so it will not provide you with tachyonic mass. But if R is non-zero, then Ricci scalar is non-zero of the flat space, even in a small region. Let me emphasize, it should not be always negative. It's enough to get a tiny, according to our current understanding. For this source, it's enough to have a tiny region of changing sign, and this will always excite some instability. Then, if R is non-zero, you may get scalarization via this mechanism. And in this paper, you may find several different classes of models, including, we try to argue that even usual electrovacuum black holes plus some corrections coming from different directions, like this f of phi, f of nonlinear electrodynamics, putting corrections to the Maxwell, or adding some stringy corrections to the Schwarzschild black hole, such that R is non-zero, may get scalarized. But the story is not, well, here I have some results, but I will skip this part. The story is not over. The situation with non-minimally coupled scalar field is really more complicated. Let's take this very simple and well-motivated, I think, Lagrangian. It's in the spirit of what we discussed before, Einstein gravity, real scalar field. And this time we are fixing this coupling constant. It corresponds to the conformal coupling. So it's a particular case such that the model has some enhanced symmetry. It's invariant under a conformal transformation. And then a few different authors in two separated papers in 74 find a black hole solution, which is very curious. It is just the extremal Reisner-Nordstrom black hole. This is the famous BBMB black hole solution, which appears for a very different, so this geometry is realized for a different matter content. It is another situation which is possible in the context of hairy black holes, same geometry realized with different matter fields. Scalar field here diverges at R equals m, the horizon, extremal horizon, but there are a number of arguments. This is not an issue. And this is a very interesting solution because does not appear as a result of scalarization. So it's a non-perturbative solution. There is some computation, people claiming it is stable, but also some contrary claims in the literature. I don't have a very defined opinion. At least it is a very interesting exercise to consider and try to understand. There are various nice features. So, but again, this is not the usual scalarization, but it shows that this type of coupling may lead to very different features. Now I have a few slides which are again on the subject of hairy black holes, few comments in fact. We have seen that usual well, this kind of non-standard, going to non-standard couplings allows to circumvent a number of well-known results in general relativity. But all these solutions, including this cubical black hole, still possess this Z2 symmetry. They possess a reflection with respect to, they have an equatorial plane, and then you can take a reflection, and everything doesn't change. But going to more complicated models allow to circumvent even this feature. And there are various mechanisms within the same class of models we discussed before. In particular, if you can find such solutions without a Z2 symmetry, even for the simplest case of Einstein-Maxwell dilatonic black holes. And there is even an exact solution found by Rashid around 15 years ago for a special value of the dilatonic coupling constant corresponding physically to a rotating diode. And then the horizon may get very deformed. This is a picture illustrating the shape of the horizon as embedded in the Euclidean tree space. You can see such a diagram has no equatorial plane. So again, it's another illustration of the fact that if you look carefully enough, more or less, most of the basic results from the electrovacuum case can be circumvented. There are also black holes without Z2 isometries. Okay. So, and the same, of course, there are other models we can discuss if you like, more general mechanisms, more general Lagrangians supporting the same mechanism and the same result. But this is the simplest one, and in particular, we have exact solutions. That's the advantage. Now, what about spin 2? Do we have a kind of tensorization? Is it possible to get similar results going to extensions of Einstein gravity? And indeed, this is the case. There is a very curious paper. I found it very interesting, written, well, 7 years ago by these authors, PRL. The Lagrangian is extremely simple. You don't have any scalar fields, nothing. You are just supplementing. It's a version of R square gravity. You are just supplementing Einstein term with Weil square in the end. Theory is will contain higher derivatives, so there are all kinds of problems because of that. But still, there is a fantastic feature. Schwarzschild is inside, also Kerr. But it's not the only solution. And it's, these people discussed, the authors, spherically symmetric configurations only. And what is fascinating, Schwarzschild black hole gets an instability because of the presence of the Weil square term in the Lagrangian. Oh, sometimes it works, this beamer sometimes. Yes. So you have this extra piece in the Lagrangian. And for a critical ratio between this parameter, which is dimension length square and mass square of the black hole, Schwarzschild black hole, you find a bifurcation of the usual Schwarzschild solutions towards a new branch. So in addition to Schwarzschild black holes, you find tensorized black holes, if you like, or how to call them. New branch of solutions, bifurcating for a critical configuration. This is the mass versus temperature diagram. It's the well-known diagram for Schwarzschild, but then we have a new branch of solutions, in which case GRR GTT is not -1, so they violate this Schwarzschild property. But such solutions, as I said, are not really physical. They likely possess a lot of pathologies. They contain higher derivatives. In particular, for some ranges, you find the negative entropies, this Wald entropy, which is a very curious feature. But still, perhaps this is an artifact of truncating the full theory to this order. But it shows, in any case, that there are still a lot of unexpected features, new classes of solutions, at least at this level. And now let's try to start. We still have 7, 8 minutes now, something like that, or 10 more. Let's try to summarize all emerging picture and discussing open problems. For example, these are standard fields with usual coupling. We don't go to scalarized black holes. Let's finalize, in fact, with scalarized black holes. They are very interesting, but there is still not very, except for this non-minimal coupling with rich scalar, in my opinion, a clear origin of these non-standard couplings between scalar field and geometric invariance or Maxwell is still missing. So we are postulating some types of couplings, non-standard, which results in non-standard Lagrangians. They are interesting. There are a variety of new features, but they are not usually not very well motivated, starting from some basic physical principles. That's, in my opinion, a problem. Although it results in normally in good quality work, in interesting results. Okay, but if you restrict ourselves to models with a very well-motivated origin, models which enter the standard model of particle physics, for example, a single complex scalar field, then massive complex scalar field, usual Bekenstein type arguments, usual Neuer theorems are circumvented by going to this synchronization mechanism, considering spinning black holes and you get scalar hair, which is connected to boson stars on one side and with the superradiant instability to the other side. So I think this is a well-motivated violation of the no-hair conjecture. For spin 1, we have abelian proca with interesting features, very similar to scalar field before, but there is also this class of colored black holes with non-abelian gauge fields, which were found in the 90s. So again, the no-hair conjecture is violated, at least the spirit. And then if you combine spin 0 and spin 1 and go to gauge scalars, then again we have violations of the no-hair conjecture from various directions. First, there are these sphalerons, monopoles, and so on in standard model of particle physics. And more recent, you can get hairy black holes, spherical hairy black holes, even with an abelian gauge field, and a single complex gauge scalar field. Now, something is missing in this diagram. You may ask, what about this part here in the middle, spin 1/2, fermions, Dirac fermions? Well, this is the only part which we know for sure it exists in nature, where the no-hair theorem still hold, still resist. To the best of my knowledge, there are no examples of black holes with fermionic hair. So there are a number of no-hair theorems found in around 2000. In the simplest case, forbidding the existence of hair for spherically symmetric black holes. And these theorems still resist all attempts to circumvent, at least mathematically. You may claim, and I agree with you, this is more a mathematical question, but it is still an interesting one, why you cannot put together fermions with a black hole horizon. So the fermionic hair is automatically disappears, and the spirit of the no-hair theorems are respected so far for such case. Of course, you can go for Ralita-Schwinger, spin 3/2, but the situation there is still less explored. And what is interesting, as a final comment, here you can find solitons, but there is no mechanism so far to support the black hole horizon and still keep the fermionic fields outside the horizon, a non-trivial fermionic field. Okay. So, questions so far? Not yet. Okay. Oh. So let's try now to return to the starting point of our lectures. In electrovacuum, there are a number of uniqueness theorems which were found as a collective effort of several great physicists, mathematicians. You have only Kerr-Newman as a physically interesting solution. Let me emphasize one point I didn't mention. There are other solutions. You can put all these monopoles, all of these multipoles on the top of Kerr solution, or Kerr-Newman, but they will possess pathologies. Something will be singular, horizon, z-axis, or at infinity, not asymptotic flatness. That the only physically relevant solution is Kerr-Newman. And this very strong result, which it's somehow surprising. It contrasts with the case of stars, of other objects in nature. It shows that the black holes, at least in the electrovacuum case, are extremely special. Gave rise to this, leads to this no-hair theorems, no-hair conjecture. Everything should be similar to the case of Kerr-Newman. You have only three numbers: mass, angular momentum, electric charge, which are found as some fluxes at infinity. It's a nice physical picture. But people extrapolated this situation to any model. This was the general expectation, and there were a number of no-hair theorems supporting this idea, found in the 70s, in the 80s. So this was the general expectation. Everything is given by a number of finite charges measured at infinity. It's uniquely fixed. That I hope I convinced you. This is not necessarily the case. It's rather exceptional. The electrovacuum case is rather very special. If you look carefully enough, it is possible to find black hole with hair in most of the models. Absence of hair is rather an exception. There are various ways to circumvent it. And let's try to summarize what is known. If you restrict ourselves, extremely conservative, to what we know it exists in nature, standard model fields, all couplings from standard model, even there, the no-hair conjecture is violated. There are black holes with gauge Higgs hair, with non-abelian fields around. However, so the spirit of the no-hair conjecture is respected because such configurations are typically unstable. They are relevant only at the microscopic scale, are interesting mathematically, but have nothing to do with astrophysics. And I provided some estimates for the wavelength of the Higgs particle. It's very far away from what is relevant on astrophysical scale. And also, we didn't find too many physical applications. But in any case, the no-hair conjecture is violated. There are counterexamples. If we are liberal enough, we are happy to consider fields beyond standard model, and also possibly non-standard couplings, like with these scalarized black holes. Then the picture is completely different from what was conjectured in the 70s, 80s, with these no-hair theorems. And there are various examples of hairy black holes. And in the last decade, I think there are at least two, well, there are many other results, but let me emphasize two clear examples and of violation of the no-hair conjecture resulting from two different mechanisms. First one holds for complex scalar field or for a abelian massive, well, Broca field, vector 1. And it's anchored in the existence of superradiant instability, which was established in the 70s. And this results in Kerr black holes with synchronized hair. So the black hole of the general relativity will possess this type of hair and could be relevant at microscopic scale this time. And the second mechanism, which attracted a lot of attention over the last 5 years, is the black hole scalarization. It holds, it's anchored in the existence of a tachyonic instability of the black holes of general relativity or more general electrovacuum black holes, which is triggered out by some non-standard coupling between scalar or vector field to some invariants. So it's, you have to accept to promote your models to non-standard Lagrangians. But it results in very different properties. Yes, I still have a few minutes, yeah? Okay. Now, let's suppose such fields, there is no, well, you may ask what will remain from this activity in 10, 20 years. There will be no evidence for the existence of such configuration. The subject will be less popular, but in my opinion, they will remain still interesting as a mathematical counterexample to some basic result, to some folklore, which was based on electrovacuum model. So the study of such configuration showed that one cannot safely extrapolate the knowledge based on electrovacuum solutions. And here I gave two examples. The shape of the horizon can be static but not spherically symmetric, or even without isometries. And the second, for example, the Kerr bound, it's a property of electrovacuum black holes. it's not universal. You can find violations and if you go to our model. So at least mathematically, studying this type of hairy black holes, studying the subject of hairy black holes is interesting. And finally, final slide. Okay, the black hole, I think I convinced you. There are hairy black holes, various models. The absence of hairy black holes is rather an exception. But still a lot of work to be done. And the main problem, in my opinion, is the last one. What is the contact with reality? Are there fields in the nature other than standard model, what we know? So this is important if you want to make contact with astrophysics, with observations. Okay, so I better stop here. And many thanks for your attention. Thank you very much.
Thank you very much, Eugen, for this very nice set of lectures. We have time for questions, so if there are questions, I see one by Roldo. I'll pass on the microphones.
Thanks, Professor Eugen, for the very nice course. My question is about these black holes without any isometries. Can you define a kind of generalization of light rings in this case? So generalization in the sense that they are periodic orbits in a certain plane?
I suggest to discuss with Pedro. We are thinking about that. There is no work. These results are recent anyway. They were found just before Corona, I think. So, yeah, thank you. It's a very good question, but I have no idea. One comment only. Just one comment. Don't forget they bifurcate here from right and north. So in some, they should, at least for some range, keep some features from there.
Yes, yes. So in some cases, can you define, well, in this case, you don't have any isometry. But can you define a Z2 isometry in this case? So
they still possess a Z2.
The event horizon, for instance, depends on the phi, on the theta coordinate, but you have this reflection symmetry.
All these examples without isometries possess a Z2.
Oh, okay. So this
but
kind of...
as I mentioned, there are, solutions without Z2, but not without... So far, we are not put together, these two features.
I see. Okay, thanks.
Okay, we have time for the questions, comments. Kai, you want to say?
So thanks for the nice set of lectures. So I was wondering, this last part about fermions and about hairy black holes with fermions caught my attention. But also because I was thinking about not hair, properly saying, but some types of configurations that might acquire like effective hair, you know. So we were mentioned a couple of days ago about these long-lived fields that could harbor around black holes. And and then maybe you don't have a hairy solution, but you have something that is for sure is not a Schwarzschild black hole. And also for fermions, I think you do have these quasi-bound states that could live there for a long time. Do you think that there is at least like an effective way to try to describe a black hole that's not Schwarzschild, is not hairy black hole, but temporarily is at least a solution?
I think Juan Carlos here in audience is much better qualified than me to answer this type of questions.
I was actually thinking about your paper that he had this.
I never really work on this subject, so my expectation in some of these solutions could be a proxy, some approximation perhaps of such configurations.
Yes.
Well, I cannot go...
Because I think the only way that I can think of how directly find one of those solutions is through perturbative means. Like, so in GR, if you perturb, so if you search around for a monopole perturbation, you only find a mass shift, right? A change in the horizon. But if you add some type of perturbation that could oscillate there, you would find that this mass is actually from the matter field that's around there. But maybe it's, I don't know, I think that it would be at least in the transition between searching for a fermionic hairy black hole or something.
Yeah, well, I think we better keep, yeah, it's a very interesting subject. I would like to know your opinion, but perhaps after the presentation, yeah. I mean,
Thank you.
I didn't know this work.
Thank you, Caio. Thank you, Eugen. So is there's a question online, I think, by Sergio.
No, it's not by Sergio, it's by me, Renan. Okay, can I ask? Can you hear me?
Renan? Então, Renan,
Yes.
please, go ahead.
Okay, can you hear me now, right? So first of all, thank you, Professor
We
Eugen.
cannot hear very well.
Well,
Please go
now
ahead.
you can.
Yeah, we can hear
Can
you
you
now.
hear me now?
Yes.
Okay, perfect then. Okay, so first, thank you, Professor Eugen, for the very nice lectures. I don't know if my question is a naive question, but you showed some black holes, scalarized black holes with different shapes of the horizon. But those scalarizations can induce, for instance, topological changes in the event horizon, because all the scalarized black holes that we showed have the S2 topology, basically.
That's an interesting question. So to answer, try to provide a partial answer. In asymptotically flat case, 4 dimensions, I think all known black hole solutions, hairy or not, in any theory of gravity which are known in this moment, to my knowledge, have an S2 topology. And to change the topology of the subject, so there are a number of theorems showing this property. One assumption being energy conditions, which you may say can be violated in some of these hairy black holes models, yeah? But there is, to my knowledge, there are no such configurations. Changing the topology of black horizon, black hole horizon requires some, I'm not sure if it can be done. I think it cannot be done without some pathologies, some singularities. So there is I don't think there is any evidence for changing of the topology in any process of scalarization. I know people found in some dynamical simulations of electrovacuum black holes some transient dynamical states with a toroidal topology. So even without going to hairy black holes, but this is highly dynamical. But in any case, here we don't have any indication. But it's an interesting subject, the topology of a black hole horizon, I agree.
Thank you.
Okay, so let me close, but before let me make a comment. So for the benefit of the audience as well, since Eugen, you were asking about fermionic hair. Well, there's actually an example where there is fermionic hair, and that's in supergravity. So you can, and since we are talking about the matter of principle, so if you have supersymmetric solutions, you can use the non-killing spinors to promote a hair on a supersymmetric solution. This was an industry act back in the 1990s, and there is a paper that I wrote in 2001 where I've done this for the BMPV black hole. So it is somewhat strange because you are actually doing it with Grassmannian variables, but you can do it. And so there's at least that class of examples where you have fermionic hair. Okay, so I'll close here, thanking Eugen for the set of lectures. Thank you very much.